Chlorine is often used for various purposes, such as cleaning water. Chlorine also happens to be a nonmetal, but has conductive properties, as seen by various studies that show that chlorine conductivity has a linear correlation with the concentration of chlorine in a solution. Furthermore, metals have been shown to have a consistent tendency to conduct electricity. So, the question remains, what would happen to the conductivity of metal chloride salts, such as iron 3 chloride? If the conductivity of the chloride salts is measured, then the conductivity will change, with non-transitional metals having the most consistent patterns and transitional metals varying on their respective changes. To figure this out, the following must be gathered: a beaker, distilled water, a conductivity probe and a lab quest, iron 3 chloride, potassium chloride, magnesium chloride, ammonium chloride, and an object to record data with. Once those have been gathered, you can proceed with the following lab. Take your beaker and fill it with 100 milliliters of distilled water. Plug your conductivity probe into your lab quest and make sure it works properly. Measure its conductivity by submerging the conductivity probe into the water. Once you have done such, take one of the metal chloride salts and put 1.75 grams of such into your beaker. Once fully dissolved, measure the conductivity of the solution in the same manner as the water. Repeat this until all of the chloride salts have been measured for a specific gram measurement. Do this over until data for 3 grams and 5 grams have been collected as well. The results from doing such are shown on screen. Iron 3, magnesium, and potassium chloride all shown to have a similar trend, which an increase in conductivity by 3.00 grams measurement, then lowest number on the 5 grams mark. However, ammonium does something else. Ammonium goes on a downward trend, only to increase back at the 5 gram mark. Magnesium and potassium are both non-transition metals, meaning that the changes in conductivity would be more likely to change due to solubility and concentration, as opposed to ammonium, which is a non-metal that acts as a metal. Iron is a transitional metal, however, and can vary depending on how many electrons are required to balance any given compound, which can cause some difference based on concentration. Furthermore, the ionic radii of metals could have affected the conductivity due to the spacing between the ions. Overall, the properties of a metal have an effect on the conductivity. Testing the chlorides in the water showed a general trend to each grouping in rising and dropping. As seen in the data, for example, potassium and magnesium both fit into the grouping of non-transitional metals and have the same trend of rising when measured at 3 grams but lowering back when measured at 5 grams. So in this way, our data turned out different than our original hypothesis, but these trends observed follow along with how we said the salts would react more than the solids, as the elements, being in different physical and or chemical forms, add variables that will change the conductivity for salts to be greater in this case. The slower vibrations of a denser solid can affect its conductivity. Limitations of the experiment involved the usage of the metals alone being inaccessible, as well as the fact that we were also limited not being able to use enough salt of the water, or to make the water completely soluble, which can be fixed with larger sample sizes and areas. Some avoidable errors could include an incorrect environment for testing conductivity, as well as a faulty lab quest. Other experimentation can be continued in these ways, and through this lab, we've discovered ways of grouping these things and reassuring to laws such as the definition of conductivity, and conductivity can relate to many other elements and compounds to be tested in the future, as many different things have many different properties and means for testing.